Thanks for coming, everyone. It's really good to see this many people here. My name is Mihkel. I'm a postdoctoral research fellow here at IOA, and I work on the formation of planets. Specifically, I try to understand how the formation environment of planets affects their composition, and I spend a lot of time studying the chemical composition of planet-forming material. So, in view of the approaching Christmas and all the meals that everybody will be having, kind of have a slightly food-themed talk on what is the food that planets eat, and as in humans, does the food planets eat also affect the outcomes in planets? Does it affect what the planets are actually like at the end? So just to start with a little bit of context, right? This is a condensed view of the solar system where all the planets are shown to scale, but their distances are not. And what you immediately see is that close to the sun, of course, we have 4 rocky terrestrial planets, Earth-like planets as we might call them. They are about 10,000 kilometers across and very, very dense. Then you go further out, you have the gas giants, Jupiter and Saturn, which are hundreds of times more massive, larger, and contain a large amount of hydrogen gas, which the rocky planets obviously don't. If you go even further out, you have the so-called ice giants, Uranus and Neptune, which are something in between. They do have, probably initially they had rocky cores, which grew massive enough to accrete some gas, but not quite as much as Jupiter and Saturn. So this is the diversity of planets in the solar system. You already see that in their bulk composition, there are quite significant differences. But as you probably are well aware, we now know of thousands of planets around other stars. And I just pulled this table from exoplanets.org earlier today, where currently the tally of planets we've identified stands at around 5,500. And this is expected to more or less double in the next few years. So there's this huge sample of planets. And what we'd really like to now begin doing is not only cataloging them in terms of how many there are, what are their sizes, but also what are the details of their chemical composition, because that is what we really care about if we want to, say, understand how common habitable worlds are in the universe. So, for humans, the Harvard Medical School has put out this very nice healthy eating plate. So this is if you want to be more or less a healthy person, the kind of proportion of foods you should be eating. And so I'd like to frame this question on this background of what is kind of the healthy eating plate for planets, what provides all the essential nutrients. And for that, we go back all the way to the fundamentals. So this is the periodic table of elements. Many of you will be familiar with this. And it's a particular version of the table where the color scale indicates, by the way, is there anybody here who's colorblind? I should just in case point out that there are 2 squares which are red, the beryllium and boron, so number 4 and 5. They're different from the green. So this shows you the origin of each of the chemical elements, and the colors illustrate what proportion of that element comes from what source in the universe. So we have hydrogen and helium, which are dominated by Big Bang nucleosynthesis. They've been around since the beginning of the universe. But you have other sources, such as mainly different kinds of stars. So as you know, probably, in stars there's nucleosynthesis, nuclear fusion happening. In the intense pressures at the centers of stars fuse nuclei together to form heavier nuclei, releasing energy, which is the energy source of stars, or it is the way of converting the contraction energy into photons, light. You have exploding massive stars, which basically means supernovae. These are even more energetic phenomena during which you can synthesize during very short amounts of time nuclei that normally cannot be made in high abundance inside any star. You can have exotic scenarios like neutron stars, so the dead cores of 10 to 20 solar mass stars perhaps. When they merge, those explosions can give rise to particular nuclei. Type 1a supernovae, so exploding white dwarfs, which are the remnants of sun-like stars that accrete material from a neighboring star and then explode. And then cosmic ray fission, so that's a fairly rare for it to be significant, but in some cases it can be very significant, and this essentially means high energy particles flying around in the universe, striking existing nuclei and breaking them apart. So there's a diversity of sources for chemical elements, and the balance between these changes as the universe evolves, although we won't go into that in great detail. So you take all of this, you put it in a galaxy with hundreds of billions of stars, and then all these atoms are floating around between the stars. You stir, and you get turbulence, you get condensations. Denser regions, these are molecular clouds, mainly molecular hydrogen, but then about 1 part in 10,000 is other atoms and molecules, for example, carbon monoxide. And here you see the Orion star-forming region, so the well-known Orion constellation with the belt of Orion and the sword of Orion there. And if you look at this with infrared eyes, you see that it's all full of star-forming clouds, which here the emission you see is actually dust, which is glowing at a very, even though it's very cold, perhaps minus 100, 170 or minus 200 degrees. But it's glowing enough for us to detect the infrared radiation. And you see these condensations, which are then the denser regions of molecular clouds where stars are forming. We zoom in even further, and every region of this cloud contains hundreds or thousands of stars that are being born at the moment. And I won't go into this in great detail right now, but this is a way that the elements make it from these diffuse clouds into condensations, which then become gravitationally bound. They collapse, forming a star at the center, and then around the star there's a disk of material. The reason this happens is because all the gas that's flying around in galaxies is turbulent, so it's just being churned around. And when you take a random chunk of one of these clouds, then it will have some randomly oriented angular momentum. So when it becomes gravitationally bound and collapses, it's easier for it to collapse along the axis of rotation, but it will like to keep rotating, so there will be some amount of centrifugal support. And so you get a disk and a rotating star at the center. So what's shown here is a cross-section through one of these protoplanetary disks or planet-forming disks. And on the right-hand side, there's just a general illustration of the fact that the part of the disk which is closer to the young star is very hot. It can be 1,000 to 2,000 degrees, enough to evaporate even rocks. And as you go further out, perhaps beyond the orbit of Earth and towards the orbit of Jupiter, then you start getting more and more ices. So all this essentially means is that molecules which are harder to evaporate, that are easier to evaporate than rocks, finally can condense out. And it's not only water ice that you get, but you get ices like carbon monoxide, carbon dioxide, ammonia, molecular nitrogen, etc. So there's this overall kind of temperature structure and a chemical structure as you go away from the star. On the left-hand side, there's an illustration of just the main components and some of the main processes happening in one of these disks. So the entire disk, even though it's rotating, it's gradually accreting onto the central star. And it's mostly a disk of hydrogen, but about 1% of the mass is in little rocks, little pebbles called dust grains. And these are the things which start out microscopic in size, less than a tenth of a millionth of a meter, so 0.1 micrometers. Over time, over 10,000 years, 100,000 years, these dust grains collide. Sometimes they stick, they grow, and this process happens again and again until these grains grow from microscopic sizes all the way to something like a meter. And eventually, these rocks come together and form the cores of planets, which are perhaps the size of something like the moon. And these, upon colliding with one another, eventually form planets like the Earth. So you have this growth, many, many orders of magnitude from microscopic dust grains. We are literally sitting on a big pile of dust. This process happens with different efficiency, different speed, closer to the young star, further away from the young star. And as you can imagine, if these dust grains are growing in a region where ices can form, so for example, you're already far enough from the young star that water can freeze out, you will not end up with pure rocks, but you will end up with some kind of mixture of rocks and ice. For example, people often say comets are dirty snowballs, so this is one way of thinking about that. There are regions where you form volatile, rich solids, is what we say. Rocks that are rich in compounds that are easy to evaporate. So there's a chemical diversity to the planetary cores that you build at different locations in the disk. All right, so why do we care about this? Well, as I indicated in the beginning, we know of many planets around other stars, and obviously about the Earth we know that it's habitable, we're here, but it's the only planet for which we know this confidently. And when people talk about habitability, whether a planet is suitable for life, very often they focus on, is it warm enough? Is it at the right distance from its star that, for example, liquid water could exist? And we think liquid water is very important for life. But it's very likely that there is a deeper level of complexity to making a planet habitable. You not only need water, but you need elements like carbon. Perhaps you need the planet to be able to form a molten core. That in turn may tie again into the average composition of the planet. Can it form the core fast enough during its early evolution? Can it ever form a core? Is there enough carbon? Is there too much carbon? So all these questions may become important when we truly try to understand the probability of a planet being habitable, suitable for life. But there are other reasons as well, and one of the main ones is when we observe a planet around another star, sometimes we find them in strange places. So you may be familiar with planets like hot Jupiters. These are giant planets, Jupiter-mass planets, that are 100 times closer to their star than the Earth is to the Sun. These planets are in locations where there would not have been enough mass by far to form them where they are now. So they must have migrated from somewhere further away from their star, very close in. But from where? There are theories, there are models that say how this process happens. But in order to test those models, it would be useful to have some kind of diagnostic that you could observe a planet, measure something about it, and then relate that to a formation location. And composition may be one of these diagnostics. So I've already told you about these, what we call snow lines, essentially different distances from a young star where different molecules freeze out from the gas. And I'll see if I can find a pointer. This magic one looks quite nice. So this is, imagine a young star here, this is distance away from the star, and what's plotted on the y-axis is the ratio of carbon atoms to oxygen atoms. And the solid line, so focus on the red solid line, that shows you the ratio of carbon to oxygen in the gas. So everything that's in the gas phase, all molecules, all atoms, if you count up all the carbon atoms and count up all the oxygen atoms and you ratio those, then that's what you get, the solid line. The dashed line is the complement of that, which is in the solids. So the reason this looks like kind of a step function is as you go further away, different carriers of carbon and oxygen go away from the gas and into the solids. And I've just written down there silicate minerals which contain oxygen. When those go into the solid phase, then the gas phase carbon to oxygen ratio increases because you lose oxygen. You go, for example, to the water snow line. That means beyond this line, water is frozen out onto solids. It forms a solid, so the carbon to oxygen ratio in the gas, again, increases, and so on. So you can see that this might provide some kind of diagram where if you measure the carbon to oxygen ratio in a planet, you can perhaps read off the formation location. So say it's a gas giant. The gas giant forms when a solid core becomes massive enough, 10 Earth masses or so, to just uncontrollably accrete gas from around it. So the carbon to oxygen ratio of a gas giant should reflect the carbon to oxygen ratio of the gas at the location where it formed. So perhaps something like this will provide the tool to tell us where a given planet formed. And you can make this diagnostic more robust by adding other elements. So to basically get more diagnostic power, more ratio lines like this, by adding elements like sulfur and nitrogen. So if we think about the bulk composition of this disk and star, then the star just contains everything it formed from. Everything is evaporated. When you measure the composition of the star, then you know what kind of total composition you started out with. For rocky planets, the overall composition reflects the overall composition of the rocks, the microscopic dust that grew to form their cores. Giant planets would be overall similar to the star because they've accreted both the solids and then the gas on top of that. But this process is actually somewhat more complicated. Once the planets are formed, during their formation and after the formation, they keep accreting planetesimals, asteroids and comets in our modern solar system. And there would have been initially many more of these. So you may form a giant planet and make it pristine out of the gas in its immediate neighborhood. But you give it a few 100 million years, and it may accrete a large quantity of small planetesimals, which are enough to basically pollute its envelope with different elements. So you add another degree of complexity to modeling all of this. So it's not quite as simple as reading off something from a diagram. So this is the Earth, a water-rich planet. And Earth is very hospitable to life. Life on Earth is based on carbon. We think carbon is the best element for forming life because it's the only one out of which you can construct these wonderful, very complex molecules that you need to encode the information of life. Yet, Earth, when you compare with the Sun, is actually incredibly poor in carbon. It is depleted in carbon by about a factor of 10 to 1,000. This underlines how carbon is truly the best element for making life. Because surely, if any other element was as good for being the foundation, then life would not have chosen the one which is so incredibly rare. But why is this? If we just hop back to this figure for a second, at the formation location of the Earth, we definitely do not see a very strong depletion, a very strong lack of carbon in solids. So there is something which removed all the carbon from the Earth. And in fact, we know the composition more or less of the surface of Mars. We know the compositions of some of the asteroids that orbit near Earth. And those are all carbon poor. So some kind of process in the inner solar system made this story much more complex than the simple kind of radial variation that's suggested by this figure. I'll get back to that in just a second. This is Jupiter. And you're probably quite used to seeing a picture like this, perhaps with a great red spot on it as well. You may be aware that now there's the Juno mission orbiting Jupiter, which is returning incredible new data, new detail. And I just really love this, this picture of a kind of storm with these huge 1,000-kilometer scale cloud features, which really dwarf anything on Earth. And these clouds, these white clouds, the beautiful features, are probably ammonia and water clouds. And the reason I mention water is because we actually don't know the oxygen content of Jupiter. So if we wanted to test our idea that perhaps the carbon to oxygen ratio in a giant planet is connected somehow to its formation location, the closest giant planet we have, we actually can't use it to test any of this because we don't know its oxygen content. Turns out that it's very tricky to measure, and Juno is, well, the scientists working on Juno are hard at work trying to do that. But we do know Jupiter's content of other elements. So I've highlighted here again carbon, oxygen, and sulfur, just like for Earth. And Jupiter is enriched compared to the Sun by about a factor of 3. So initially, I said a giant planet would just accrete everything into it, so it should more or less have the same composition as the Sun. And here we see an enrichment. There is also a tentative enrichment in sulfur and definitely enrichments in various other kind of elements that like to form ices or gas, like krypton, argon, etc. So I already indicated that this is most likely due to Jupiter's accretion of cometary bodies, asteroid-like bodies, after its formation. It really underlines the complexity of understanding the details of a planet's origin, because it all gets so mixed up. So just to summarize this point and get close to the end now, for Earth, the idea of what might have caused Earth's early carbon runs is in fact the same as this figure, sorry, I'm scrolling back, as this figure here. But we have to keep in mind that when the solar system was forming, the temperature structure as a function of radius was not fixed. In the very early stages, the solar nebula, the planet-forming disk, would have been much, much hotter. And so in fact the idea is that just before the Earth formed, the disk was so hot that all the solids were evaporated to a much larger distance. So then eventually you ended up with this very carbon-poor mass of solids that then grew into the Earth. And the timing of this is something that we hope to constrain with models eventually to really pinpoint the formation history of Earth. For Jupiter, I already mentioned that comets and asteroids probably delivered its excess of carbon and sulfur and perhaps oxygen, we don't yet know. And these similar bodies delivered the oceans to the Earth, because as I said, if Earth formed in a very hot environment, it would not have had a lot of water when it started out. So we're very fortunate, in fact, to have ended up with all the oceans we have. So finally, I just want to highlight, for those of you that might be thinking about studying physics, chemistry, astronomy, some of the work we're doing here. This is a project that a master student, Shushmoy Rai, is currently working on here at IOA, where while most of the community studying planet formation is focused on carbon and oxygen, we're now kind of trying to take the next step and add one dimension to this chemical diagnostic by characterizing how sulfur behaves in planet-forming environments. And so if anybody's interested in that, then I'm happy to take questions on that later. So carbon and oxygen are very special. They can be measured in both exoplanets, giant planets around other stars, and in planet-forming environments around other stars. There are not many elements which we can access, which we have kind of accessible to observations in both of these environments. So that means they are very useful for constraining our models of planet formation. But it's only early days because we literally have a handful of planets and a handful of planet-forming disks for which we have any of this abundance information. So all the things I'm telling you now, in fact, are kind of a hypothesis rather than results. And so sulfur will definitely be, if not the next big thing, then one of the next big things in the chemical characterization of planets around other stars. And with that, I'll leave you with my summary.